In math, after you learned about adding, you learned about how to undo addition, which was subtraction. They were inverses. When you learned multiplication, you also learned how to undo multiplication by division. When we took square roots, we also took squares because they were inverses. Same thing is going to hold with calculus. When we have a derivative, we actually have an inverse operation, which is called an antiderivative. At the end of this lesson, you'll be able to use basic integration rules to find the antiderivative of a function. All right, let's kind of look at what an antiderivative is. What if you were asked to find a function whose derivative is 4x cubed? In other words, we are going to work the derivative backwards. What we are trying to find is called an antiderivative of a function. Okay, if we call f of x 4x cubed, let's find out what are some possible solutions for f of x such that f prime of x equals f of x. What that's talking about is, can I come up with a function so that when I take the derivative of it, I'll end up getting 4x cubed? And I will just list a couple choices. Let's say I had x to the fourth plus 7. The derivative of x to the fourth plus 7 would be 4x cubed. So that would work. Let's think of another one that would work. If I had x to the fourth minus 10. If I took the derivative of that, that would also give me 4x cubed. So both of those would be antiderivatives. You'll notice as long as I put a constant next to the x to the fourth, I really can put any constant that I want. That leads us to the general solution, which is just going to be x to the fourth plus c. So c is just any constant that I could put next to it. Right, some notations for antiderivatives. The process of finding all solutions of this equation is called anti-differentiation. Remember before when we took the derivative we called it differentiation. So this would just be called anti-differentiation. Another thing that is very common, and you'll hear me use this a lot, is the word integration. Okay, the general solution is always going to be denoted by the integral of f of x will just be big F of x and then plus c. We'll always have a plus c because you can always add a constant, because when I take the derivative of it, the constant drops out. Okay, and c is called the constant of integration. The expression above is read as the integral or antiderivative. Either word is interchangeable. They mean the same thing. Of f with respect to x. Now notice this big thing, we put dx right here, just how we put in our other when we took the derivative of the problem. This dx, although we don't use it for anything, it is important to let us know what our variable is. So as I'm working through the problem, I know the variable is x, so any other letters that might be in my problem will be constants. Okay, and just like I said, square roots are inverses, addition, subtraction are inverses, multiplication and division are inverses, differentiation and integration are inverses of each other. They undo each other. Okay, what we're going to get into now, just like when we took derivatives, we had certain rules. We also have certain rules for basic integration. Most of these rules I'm just going to show you kind of using when we took the derivative. So if you know your derivative rules, these should go quite nicely for you. Okay, so the first one, we would like to find the antiderivative or the integral of 0. And our variable is x, because that's why it says dx. So I want to think, what function that when I took the derivative of it would give me 0? Well, I know if I start with a constant, when I take the derivative, I get 0. So the answer for this one is just going to be c, some constant. Okay, if I look at the next one, the integral of k dx, notice it's dx, so my variable is x, which means k is just some number. So I need to think, what would I have to start with so that when I take the derivative, I just get a number, and that would just be kx. Notice when I take the derivative of kx, since k is just a constant, I end up with k. And then I do also need to put plus c because I could have had a constant attached to it. All right, these next rules are just ones that we'll find helpful as we're going through to use them. If I have some number, like it's a 5 or a 6 or a 2 or whatever, and it's multiplied by a function, I can always write that out front so that it's not in my way as I'm taking the integral or antiderivative. The next thing is, if I have two different functions being added or subtracted, I can always separate them into two separate integrals, and we'll do that quite often. You will notice there's not a rule if I have two functions that are multiplied together, so we actually have to do that a little bit differently, so we'll make sure that we don't do that. Okay, this next one, I'm just going to do a few examples. Let's say I would like to end up with x to the sixth. So I would look at what would be my antiderivative so that when I took the derivative of this, I would get x to the sixth. And I know I'd start out with 1/7 x to the seventh, because when I took the derivative of this, I'd get x to the sixth. Let's say I wanted to end up with x to the fourth. I'd have to start with 1/5 x to the fifth, because when I take the derivative of that, I'd end up with x to the fourth. Let's say about x to the sixth. In order to get x to the sixth when I take the derivative, oh, I already did x to the sixth, let's try x cubed. I'd have to start with 1/4 x to the fourth, because when I took the derivative of this, I'd get x cubed. So notice, hopefully you're seeing a pattern join here. When I take the integral, so this was all the antiderivative, I took the antiderivative of those, that's what I would end up with. Actually, well, I took the integral of those. Because this is what would I take when I took the derivative, I get x to the sixth. So hopefully you notice what's basically happening with the power. When you take the derivative, we subtract 1 from the power. When I take the integral, we have to actually add 1 to the power. So it's going to be x to the n plus 1, because we're going to add 1 to the power. And then when we do this, there's a couple different ways I could write this, and I'll write it both ways. We're either dividing by the new power, or you'll notice out front I always put like 1/7, 1/4, 1/6. We could do 1/n plus 1 times x to the n plus 1. And then of course both of those would get plus c. So either one of those formulas would work fine. You can just decide which one you're more comfortable with. Okay, next one. The antiderivative of cosine x. So I want to think, what would my original function be? So when I took the derivative, I get cosine. Well, I know if I start with sine, the derivative of sine is cosine. Okay, the next one, the antiderivative of sine. So what would I have to start with so that when I took the derivative, I would get sine? And I'm actually going to have to start with negative cosine of x, because when I take the derivative of this, I do end up with a positive sine x, because the derivative of cosine is negative sine. And then of course we're always going to put that plus c, because we could always add a constant to that and have it work. Okay, next one, we have the secant squared, and if you know your derivatives, these actually should be very easy to memorize. I'd think, what would my original function be so that when I took the derivative, I'd get secant squared, and that would be tangent. And then the next one, what original function would I have started out with so that my derivative would be secant x tangent x? That would be secant x. Okay, this next one, what function would I have had to start with so that my derivative is cosecant squared x? And we'd actually have to start with negative cotangent x, because since the derivative is going to be negative, we would have to start with a negative number. And the last one, the antiderivative of cosecant x cotangent x, I'd be looking for what function that when I took the derivative of it would give me cosecant cotangent, and that would be negative cosecant x plus c. So you'll basically notice the ones that usually weren't negative when I took the derivative of, they are negative when I take the antiderivative. All right, let's see if we can actually use some of these to find some answers. All right, this first one says, find the general solution of the differential equation. dy dx, please remember that that stands for the derivative, so it's telling you that the derivative of y is equal to 10x to the fourth. We just want to find y. So please remember that I said that derivatives and antiderivatives are inverses of each other. So if I want to get rid of a derivative, I'm actually going to take the antiderivative, or the integral, of both sides. Now when I take the derivative, the antiderivative of the derivative, I'll just be left with y, because they undid each other. And then on this side, couple things I'm going to do. First of all, notice that 10's there. I'm going to pull the 10 out front so it's not in my way. And then when I do this, the 10 is just going to kind of tag along for the ride. So just put the 10 down. And then we're going to use that power rule, which we're going to increase the power by 1. And then it gets 1 over that new power on the outside. So we're going to have 10 times 1/5, which would equal 2x to the fifth. And then, of course, we want to remember that plus c, because I could have started with a constant in this original problem. So that would be my general solution. All right, let's just try a few more. Notice it says to evaluate the indefinite integral. That's exactly the same thing as finding the antiderivative. You'll notice on this first one there's a plus sign, so what I'm going to do is actually separate this in two parts. Please notice when I'm doing this, I'm really not concerned about the dx. That's basically just telling me what my variable in the problem is. Okay, on this first one, the integral of x to the fifth would be 1/6 x to the sixth, because we increase the power by 1 and then multiply by the 1 over that power, new power on the outside, and then plus, since this is a constant, what would we have had to start with so that my derivative is 4? We would have had to start with 4x, and then of course we're going to put in that plus c. Okay, one thing that's nice about these problems is, since you're familiar with the derivative, if you take the derivative of your answer, you should end up with what you started with. So notice it works out nicely, and that's exactly what I would end up with. Okay, let's try the next one. Please notice that I told you that we don't have any sort of rule if there are two things multiplied together. So the first thing that I'm actually going to do on this one is distribute. So I'm going to end up with t cubed plus 3t to the fourth dt. And again, dt is just letting me know that the variable in the problem is t. There's a plus sign, so I'm going to separate into two separate parts. Please notice when I separated the second one into the part, I did just leave the 3 outside. The antiderivative of t cubed would be 1/4 t to the fourth. Again, I'm just increasing my power by 1. And then plus 3, that 3 is a constant, just tags along for the ride. The antiderivative of t to the fourth would be 1/5 t to the fifth. Okay, and then from here, just cleaning it up a little bit, I could have 1/4 t to the fourth plus 3/5 t to the fifth, and then of course we want to remember that plus c. And again, if you'll notice, if I took the derivative of this, I would end up with what I started with, so that's just a nice way to check the problems. All right, this next one, it does not look like it's in a form that we can actually take the integral, so I'm going to rewrite this as the integral of x. The 3 is the power and the 4 is the root. So this would actually be x to the 3/4 power. And then when I take the derivative of that, let's see here, this is going to be a little trickier. I'm going to do a little bit different on this one. I'm going to add 1 to my power. So x to the 3/4 plus 1 would be x to the 7/4. And then please remember, we're going to divide by the new power. We're going to divide by 7/4. Well, dividing by 7/4 is going to be the same thing as multiplying by the reciprocal of 7/4. So my answer is actually 4/7 x to the 7/4, and then again plus c. So in these ones, when you do have fractional exponents, basically what happens on the outside is we end up with the reciprocal of that new power. All right, let's try another one. Again, there's a plus sign, so I am going to separate the antiderivative into two separate parts, and I'm going to put that 3 on the outside. Now just treat each one separately. The antiderivative of x squared would be 1/3 x cubed, and the antiderivative of this one, let's bring that 3 down, the antiderivative of cosine would be sine. And if you're not sure about your signs, when you actually recheck it, if you go to take the derivative of this, just make sure you get what you started with, and in that case I would. Okay, let's try another one. This one looks a little tricky. Again, we don't have any sort of rule if we have division. So what I'm going to do instead is rewrite this. I'm actually going to move that square root of x up top. So I'm going to rewrite this as x plus 1 times, if I move that up top, it is a 1/2 power down below. So when I move it up top, it's going to become a negative 1/2 power. And again, the dx is there to let me know my variable is x. The next thing, we don't have a rule for multiplication. So I'm going to distribute, so I'll end up getting x. If you remember, if I take x times x to the negative 1/2, we're going to add the powers using our exponent rules. So 1 plus negative 1/2 would be 1/2, and then plus 1 times x to the negative 1/2 would be x to the negative 1/2. Okay, now since we have a plus sign, we can separate it into two separate integrals. Okay, and then from here, if I raise my power by 1, I'll get x to the 1/2 plus 1 would be 3/2. And then from that previous example, remember if we had a fractional power, we ended up with the reciprocal of that power out front. And then the next one, if I have x, if I add 1 to that power, negative 1/2 plus 1 would be positive 1/2. And then again, if I have a fractional exponent, I end up with the reciprocal of that, which would be 2 out front. And then one more thing I'm going to do on this problem, I have 2/3 x to the 3/2 plus 2. If I have an x to the 1/2, that's very easy to rewrite as a square root, and I'd encourage you to do that. And then of course we still need to include our plus c because this is a general solution. All right, let's try one more here. Again, I don't have a rule for multiplication, so again, I'm going to distribute. So I'm going to end up getting secant y tangent y minus secant squared y. And my variable is y in this problem, minus sign, so let's separate them into two separate antiderivatives. Okay, and then from here, if you know your rules, this is a really simple problem. What would the antiderivative of secant y tangent y be? It would be secant y, and then minus the antiderivative of secant squared y would be tangent y plus c. And again, you could always just check this. I know that the derivative of secant y was this, the derivative of tangent y was this, so we would be all set.